Can you hear me? Hello? Tell others to join first. So I'll share my screen now. Can you see the screen? Can you see the screen? Okay, Anurag. So only 24 have joined. Please tell others to join first. One more minute. I'll wait for one more minute. So I think we can start now. So where did we stop yesterday? Do you remember where we stopped yesterday? What we were discussing yesterday? Anyone? Where did we stop yesterday? Type in chat box. You don't remember what we were discussing yesterday? Yes, relations. We were discussing about the properties of relations, isn't it? The main heading was properties of relations, isn't it? And based on properties, we can classify relation into different types. Okay. We were discussing about the properties of relations. And how many properties were there? How many properties were there? See, properties, yesterday I think we discussed this properties of relations, or based on these properties we can classify relations into different types, okay. And there are basically four properties. The first one is reflexive property, next is symmetric property, then anti-symmetric and transitive. Yesterday I think we had discussed what reflexive property is, isn't it? Do you remember? We had discussed what reflexive property is, and if relation satisfies reflexive property, we call it as a reflexive relation, isn't it? Then we discussed another form of reflexive relation, that is irreflexive relation, and then neither reflexive nor irreflexive relation. So that was what we were speaking about yesterday, the first property, reflexive relation, isn't it? Then now let us move on to the next property, the second property, that is After reflexive comes, what is the next property? Why Deepika Mohan was not there yesterday? Okay, what is the next property? Symmetric. Okay, very good. Symmetric property. So what is symmetric property? Second property is symmetric property. Now, based on what this property states is, if you have a relation R is equal to, suppose the relation R is equal to 1, 2, 2, 1, 2, 2. Okay, so one relation is given. So for this relation R to satisfy this symmetric property, what the property says is that if AB is an element of R, then BA must also be an element of R. Okay. So, what symmetric property states is that a relation is said to be symmetric. This relation R satisfies this property, symmetric property, only if there exists an element AB, which is an element of R, then BA should exist. So a relation is said to be symmetric. If an element AB exists, then the element BA should also exist. Now let us see whether this relation R satisfies symmetric property. The first ordered pair is 1, 2. So you have to check if 1, 2 is there, then the property says that 2, 1 should be there. So the next is 2, 1. So 2, 1 is there. Okay, so next another element, the next ordered pair is 2, 2. Okay, 2, 2 is there means again 2, 2 should be there. So if 2, 2 is repeated, it can be written just once. So if 2, 2 is there means we needn't write it twice. It is implied that 2, 2 is an element of R. So we have 1, 2 is there, then 2, 1 is there. 2, 2 is there, then 2, 2 is also there. So this R satisfies symmetric property since this. If AB is there, BA is there. Again, this AB is there. Again, BA is there. So this relation R satisfies symmetric property. Any doubt? If AB is there, then BA should be there. That is what symmetric property says. Is it clear? Any doubt? Any doubt in symmetric property? Now let us see another example which does not satisfy symmetric property. See, another relation R is equal to 1, 2, then 2, 1, 2, 2, 3, 2. Does this relation satisfy symmetric property? Check if this relation satisfies symmetric property. Can anyone say whether it satisfies symmetric property or not? This second relation. This is R1, this is R2. Check if it satisfies symmetric property. This relation R2 satisfies symmetric property. Anyone please respond? Why Ashwin doesn't satisfy? Why Anada? Can you give the reason? Can you give the reason why it doesn't satisfy symmetric property? Why this R2 doesn't satisfy symmetric property? Give the reason why R2 doesn't satisfy symmetric property. Okay, 3, 2 is there, but 2, 3 is not there. Yes. 3, 2 is there, but the ordered pair 2, 3 is not there in this relation. So if any one element is absent, that is, you have to look at all ordered pair. 1, 2 is there, then 2, 1 is there. 2, 2 is there, 2, 2 is there. This needn't be repeated twice. Then if 3, 2 is there, 2, 3 should be there. 2, 3 is not there. So this R2 is not symmetric. If it is not symmetric, we call it as asymmetric. Okay. If it is not symmetric, then we call it as asymmetric. So we had studied two relations under this property, symmetric relation. So those relation R1 satisfies symmetric property, so it is called a symmetric relation. R2 does not satisfy symmetric property, so it is called an asymmetric relation. Is it clear? So under symmetric property, we have symmetric relations and asymmetric relations. Those that satisfy symmetric properties are called symmetric relations, and those relations that do not satisfy symmetric properties are called asymmetric relations. Is it clear? Is it clear to you now? Should I repeat? Should I repeat it? Hello? Okay. Then, shall we move on to the next property? Okay. So the next property. Now see in the notes, examples are also there. So as a definition, if we want to say a relation R on a set A is called symmetric if xy is an element of R, then it implies that yx is also an element of R. Okay. If xy or AB, you can write xy or AB any variable. If xy is an element of the relation R, then yx is also, it implies that yx is also an element of R for xy, which is in the set, for any element xy in the set A. So this is the definition of symmetric property. A relation R on a set A is said to be symmetric if xy is an element of R, then yx should be, that it implies that yx is also an element of R. So an example of a relation that satisfies symmetric property is the equality relation, equal to relation or equality relation. It is symmetric. The equal to relation is symmetric because A is equal to B if and only if B is equal to A, isn't it? If AB exists, then BA should also exist because it is equal to property. So equality relation is symmetric because if A is equal to B, then it implies B is also equal to A. Okay. Then next one, next property. Third one is anti-symmetric property. Are you writing it down? Did you write it down? Symmetric example? Did you write this down? Hello? So you do one thing, you just write lecture notes and then write the detailed notes from the notes which I had uploaded in Linways. I had uploaded these notes in Linways. Okay, so now you just write down the lecture notes and after that you take the notes from Linways and write down all the notes which I had uploaded in these online classes. Okay, write down all notes from the course materials uploaded in Linways for these online classes. Okay. So next we are going on to the next type of relation, and that is anti-symmetric relation. Third property. Third one, anti-symmetric relation. Anti-symmetric relation. Anti-symmetric relation. Now, what is anti-symmetric relation? Now, anti-symmetric relation states that if AB is an element of R, if AB is an element of R, then BA should not be an element of R unless A is equal to B. Okay, this is anti-symmetric property. That is, if AB is an element of the relation R, then BA should not be an element of R. Even if BA is an element of R, then the condition is that A should be equal to B. This is anti-symmetric property. That is, if AB is an element of R, then BA should not be an element of, is not an element of R. And if suppose if BA exists, then the condition is that A should be equal to B. Only if A is equal to B, then it can exist. If they are two different elements, that is, if in a relation R, if 1, 2 exists, if 1, 2 is there, then 2, 1 should not be there. Should not be in the relation. Okay, if 1, 2 is there, then 2, 1 should not be there. But if 1, 1 is there, then it is okay because A is equal to B. So this is okay. In anti-symmetric relation, we can accept these ordered pairs. But if 1, 2 is there, 2, 1 should not be there since 1 is not equal to 2. Here 1 is equal to 1, so it can 1 is equal to 1, so it can exist. But if A is not equal to B, then it cannot. The BA should not be there in the relation, and that is anti-symmetric anti-symmetric relation. Okay. Now let us look at an example. Let us look at an example. R1 is equal to 1, 1, 2, 2. Is it anti-symmetric? Is it anti-symmetric? Look at this relation. Is it anti-symmetric? No one is responding. It is anti-symmetric, isn't it? Because both elements, if AB is there, then BA is also there. That is 1, 1 is there, but they are equal. If A is equal to B, then it can exist. But if 1, 1, 2 is there, and if 2, 1 is also there in the relation, then this is not an anti-symmetric relation. Like another example, I'll give you. R2 is equal to 1, 1, 2, 1, 3, 2, 1, 2. Is it anti-symmetric or not anti-symmetric? Is it anti-symmetric or not anti-symmetric? Is it anti-symmetric? No. Why, Akash? It is not anti-symmetric. Why? It is not anti-symmetric. Why? I said if 1, 1 is there, it's okay because they are equal. The elements are equal. If 2, 1 is there, then you have to check if 1, 2 is there. If 1, 2 exists, then it is not anti-symmetric. If 2, 1 exists, 1, 2 should not exist in the relation. Only then we call it as anti-symmetric. Like suppose another example, 1, 1, 2, 2, 1, 2. Is it anti-symmetric? Is it anti-symmetric? Is it anti-symmetric? Yes. Why? Yes, it is anti-symmetric. What is the reason? 1, 1 is there. If the elements are equal, it is okay. It can be there. But if, and here last ordered pair is 1, 2. So you have to check if 2, 1 is there. If 2, 1 is there, then it is not anti-symmetric. 2, 1 should not exist. For the anti-symmetric property to be satisfied, 2, 1 should not exist. And 2, 1 is not there in this relation. So we say that this is anti-symmetric. It satisfies the anti-symmetric property. So if 2, 1 were present, then it is not anti-symmetric. Since 2, 1 is not present, it is anti-symmetric. Okay, so did you understand the anti-symmetric property? Do you understand the anti-symmetric property? Did you understand? Okay, so that is anti-symmetric property. Then, next property. Now we note down this point also there. That is, write down this point also, okay? If there are n elements in a set, if there are n elements in a set, then there will be 2 raised to n into n plus 1 by 2 symmetric relations. Symmetric relations possible in that set. Okay, if there are n elements in a set, if a set has n elements, then the number of symmetric relations that are possible on that set is 2 raised to n into n plus 1 by 2. This number of symmetric relations are possible on that set. Okay. So we discussed about symmetric property earlier. So according to that symmetric property, now based on symmetric property, you have to write down this note. Just note this, okay? Now how many, the first property was, what was the first property? What was the first property we studied yesterday? Reflexive. Okay. How many reflexive relations are possible on a set A with n elements? How many reflexive relations are possible on a set with n elements? Yesterday we had written it. How many reflexive relations are possible for a set with n elements? How many reflexive relations? I think you wrote it down yesterday and you calculated the value also. Just note it, okay? If a set has n elements, then there will be 2 raised to n square minus n reflexive relations on that set. If a set has n elements, if A has n elements, then 2 raised to n square minus n reflexive relations can be defined on A. Okay, if a set A has n elements, then it has 2 raised to n square minus n reflexive relations defined on A. And how many symmetric relations? If a set A has n elements, then how many symmetric relations? 2 raised to n into n plus 1 by 2 symmetric relations can be defined on set A. Okay, if a set A has n elements, then this number of reflexive relations are possible and this number of symmetric relations are possible. Okay, so write it down as notes. Points to note. Okay, the first point is if A has n elements, then the total number of reflexive relations possible on A is 2 raised to n square minus n. And if A has n elements, the total number of symmetric relations that are possible is 2 raised to n into n plus 1 by 2. Okay. Then, so we had discussed 3 properties now. The first was reflexive property. Do you remember what reflexive property is? Do you remember what reflex? Very good type. What is reflexive property? We discussed it yesterday in detail. What is reflexive property? What is reflexive property? If a relation R on a set A is said to be reflexive, if A is an element of R for all A element of A, that is, if A is equal to 1, if A is equal to, if A is equal to 1, 2, 3, then the relation R should have which all elements? The relation R should have 1, 1, 2, 2, and 3, 3. Okay, every element of A should be related to itself. That is A R A for all A element of A. Okay, A R A for all A element of A. Then it satisfies reflexive property. If A has three elements here, 1, 2, and 3, then the relation R should have 1, 1, 2, 2, and 3, 3. If any one is missing, then it is not reflexive. If one or either one or two elements are only there, then it is, we call it as, what do you call it? Neither reflexive nor irreflexive. And for it to be irreflexive, none of these elements should be there. If no element is related to itself, then we call it as irreflexive. Then, so we had stated three properties and 2 points you have noted. Is it clear? Any doubts? So this anti-symmetric relation, we have less than or equal to B is an anti-symmetric relation. Less than or equal to is an anti-symmetric relation. Okay. Example of anti-symmetric relation is less than or equal to is an anti-symmetric relation. Why anti-symmetric? Why is it anti-symmetric? A comma B. It satisfies this condition only when A is equal to B. Less than or equal to is satisfied only when A is equal to B. Isn't it? 2 comma 2. It satisfies less than or equal to relation because 2 is equal to 2. Isn't it? So since if let us see the next order pair 1 2, 1 is less than 2, so it satisfies this property. And if 1 2 is less than or equal to B, 2 1 cannot exist in this relation because 2 is greater. So this ordered pair will not exist in this relation less than or equal to. So since 2 becomes greater than 1, this ordered pair will not be there. So if 1 2 exists, then 2 1 cannot exist in this relation. So we call it as an anti-symmetric relation. If 2 2 is present, then it satisfies, since they are equal, it satisfies this relation. And if 1 2 is present, 2 1 will not be present because 2 becomes greater than 1 and this less than relation will not be satisfied. So less than or equal to relation is an anti-symmetric relation. Okay, an example of an anti-symmetric relation is less than or equal to. Is it clear? Is it clear? Also greater than, let us see, greater than or equal to. Is it anti-symmetric? Is the relation greater than or equal to anti-symmetric? Is greater than or equal to anti-symmetric or anti-symmetric? Is greater than or equal to anti-symmetric on a set of real numbers. Is greater than or equal to anti-symmetric on a set of real numbers. Can anyone answer that question? Is greater than or equal to anti-symmetric on a set of real numbers. Is it anti-symmetric? We are taking all set of numbers and just checking if they are anti-symmetric. set of real numbers and check if they are anti-symmetric. See, set of real numbers means you can take any number, okay? And let us take two numbers, say 2 and 1, okay? Any two real numbers. So this satisfies 2 is greater than 1, isn't it? 2 is greater than 1. So it satisfies this property, that is greater than or equal to property. And suppose in that relation R, can we add 1 to this relation? Can we add 1 to this relation? No. Why? We cannot add 1 to this relation. Why? Can we add 1 2? Why you cannot add 1 2 to that relation? If I add 1 2 to this relation, is it will I be able to add this to this relation which satisfies greater than property, greater than or equal to property? Akash said no. Why? Reason? What is the reason? Simple reason, isn't it? Very simple reason. I cannot add 1 2 here because 1 is 1 greater than or equal to 2. No, this is not satisfied, so this ordered pair will not exist in this, isn't it? So if 2 1 is present, 1 2 is cannot be present in this relation. So in that case, we can say that it is anti-symmetric. Suppose if 2 2 is there, if 2 2 is there, 2 2 can be present because it is this equal to is satisfied. But if 2 1 is there and 2 is greater than 1 is satisfied, but I cannot add the ordered pair 1 2 to this relation since 1 is less than 2. Okay, so this property greater than is not satisfied in this pair. So whenever 2 1 exists, 1 2 will not exist in this relation, and that is what symmetric property says. If AB exists, BA should not exist unless A is equal to B. So this greater than or equal to also satisfies anti-symmetric property. Then less than or equal to also satisfies anti-symmetric property. So two examples of anti-symmetric relations. The two relations are those relations that satisfy greater than or equal to property and less than or equal to property. Okay, two examples of anti-symmetric relations are those relations that satisfy greater than or equal to property and less than or equal to property on a set of real numbers. Okay. Is it clear? Now write down this question and you have to work it out as an exam, as a homework. Okay. Write down this question and work it out as a homework. Let A is equal to, let A is equal to 1, 2, 3. All these questions which I'm giving you as homework, you will have to upload it in Limbase. Okay. Let A is equal to 1, 2, 3, and R1 is equal to 1, 1, 2, 2, and R2 is equal to 1, 2, 2, 1, 2, 3. Okay. Please write down the question. Then check if the relations satisfy, reflexive, symmetric or anti-symmetric properties. Check if the relations satisfy reflexive, symmetric or anti-symmetric properties. Check if the relations satisfy reflexive, symmetric, or anti-symmetric properties. Okay. Did you write down the question? Okay, Agash. Okay. That was the reason. So now, did you write down this question? Did you write down the question? Please write down first. Now let us move on to the next property. One more property is there, transitive property. Please write down this question or take a screenshot. Now let us move on to the next. Okay, Nivedita. The fourth property is transitive property. Fourth property is transitive property. Now, transitive property states that if in a relation AB exists and BC exists, then AC should exist. Okay. See, I'm not giving you the set notation definition. I'm just giving you the statement which you should study. If you study this, then you will be able to understand what this property is. Just remember this sentence and you will be able to understand this property. But when you define what transitive property is, you have to look at the textbook, the notes, the course notes definition. Okay. So, in transitive property states that if in a relation R, AB exists and BC exists, then AC should exist. That is, if A is related to B and B is related to C, then A is related to C naturally, isn't it? That is, let us see what this property exactly means with an example. That is, if 1 is greater than 2 and 2 is greater than 3, then 1 is greater than 3. This is the simple example of transitive property. If in a relation or if it includes ordered pairs which satisfies this greater than relation, then it will have 1, 2, 2, 3, 1, 3. Okay. So looking at this, if 1, 2 is satisfied, 2, 3 is also satisfied in the relation, then you should check if 1, 3 is there. If 1, 3 is there, then we can say that R satisfies transitive property. Is it clear? You have to check if 1, 2 is there. Next, you have to check if 2 is related to some other element. If 2 is related to some other element, then this 1, 3 should be there in the relation. So 1, 3 is there. Then this is a reflexive relation. Then this satisfies the transitive property. Is it clear? Is it clear? Is it clear? Did you understand what transitive property is? So we'll do the examples in the next class. Now say your attendance. Number 1.
1.
2. 2 absent.
3.
4. Next.
5.
6.
7.